Welcome to the IoT Dev Chat, a production of insight.tech. I'm Kenton Williston, the editor-in-chief of insight.tech and your host for today's podcast. This podcast was recorded during quarantine, so you may notice some differences in audio quality, as well as possible guest appearances from pets and kids. But we're glad you could join us either way. Let's get into the conversation. In today's podcast, we'll look at the latest in machine monitoring and discuss ways AI and machine learning can give engineers superhuman capabilities. Plus, we'll talk about NASCAR. No, really, I promise it will all make sense. I'm joined today by Joe Speed, Field CTO for Global Partners and Alliances at ADLINK. Joe, please tell me a little bit about yourself and your role at ADLINK.
Sure, happy to. Ken, real pleasure to meet you today. So my name is Joe Speed. I'm the Field CTO for Global Partners here at ADLINK Technology, a Intel partner. For myself, I'm a long-time machine-to-machine Internet of Things nerd going way back. Spent several years taking an obscure telemetry protocol and getting it made open standard, open source, and convincing people to use it. So that's MQTT, which is now the IoT on-ramp for Amazon, Microsoft, IBM, Google, and most others that matter, and is built into all the cars and is in most of the things. I'm also very passionate about cars. I like cars. And so one of the great things is I've, over the years, convinced a lot of companies to let me build cars. So with Intel, I've actually built quite a few advanced technology concept cars, cognitive cockpit, autonomous vehicles, accessible bus for elderly disabled, a lot of things. So very long relationship working with the Intel technologies and the people there.
Very, very cool. And of course, I'm sure I'm not the first person to observe with a name like Joe Speed. You're sort of forced to get into cars, huh?
Well, it is kind of a prerequisite. We'll see. My son is Dash, so we'll see what he does. And
wow, that's great.
And I come from a long line of family, people going fast. So my entire family, except for myself, they're all military pilots.
Oh, wow. Amazing. Amazing. So you mentioned cars, and we recently interviewed you for an article about cars, specifically NASCAR, the racing series for our international listeners who are not familiar with that. And it's definitely worth checking out, but I have to ask, what in the world NASCAR has to do with machine monitoring?
Well, it has a lot to do with it. So NASCAR cars are machines, and they are made by machines, and they are tested by machines. And, I've spent some time in the past at the NASCAR R&D site and then working with some of the racing teams. And what's kind of amazing is how much technology, how much like really current and cutting edge technology goes into the design, manufacturing, testing, and monitoring of such an aggressively low-tech product.
The funny thing about NASCAR, of course, is that it is, like you said, aggressively low-tech. It's coming from that whole race it on Sunday, sell it on Monday mentality. And of course, the cars are not really all that similar to road-going cars these days, but that is the legacy still, is having a very low-tech approach to racing.
Sure, but the part that they don't tell you is that the trackside pit box is a rolling data center stuffed full of Xeon CPUs. They don't tell you about streaming the telemetry in real time to the team operations center where they're doing the analytics, streaming analytics. They don't tell you about all the, FP64 fluid dynamics analysis in simulation for the airflow, calculating grip coefficient across all four tires. These are all the things that they don't really tell you about.
Yeah, and in our article, you talked about how engine failures are a huge, huge deal. And I think you said it was like $250,000 for one of these engines. So you want to monitor them very, very closely to make sure there are no problems while they're out there zooming around the track.
Yeah, so certainly monitor during race, but even better is to go in the race with a hardened product that's free of defects. So you think about optical inspection, having very precise controls during the manufacturing, optical inspection during and after, test to destruction on samples of units, being able to intercede with test situations so that if there is a failure, you get clean breaks, you can inspect under microscope, all of these kinds of things.
Yeah, totally makes sense. So what is ADLINK doing to help put together a really robust engine and keep it from failing on the track?
When you look at a NASCAR engine, what is an engine? It's rotary machinery. And, we have a long history of working with such things. Like we do, our company, ADLINK, it stands for Analog to Digital Link. So the company was founded doing high quality analog to digital data acquisition devices, what have you, right? So we manufacture things for the test and for the testing instrument industry, things like doing analog to digital at 2 million samples per second, things like doing analog to digital at 256,000 samples per second per channel across many channels into 24-bit digital. So we're capable of generating, quite large amounts of data. And once you have the data, you need to do something with it. So you look at our edge compute business, the things that we do around manufacturing the rugged edge compute, now edge AI with the hardware accelerated ML and analytics. And so, this is how it all fits in. So really the same technologies that we use with the NASCAR engines is the same technologies that we deploy on factory floor that are used with 50 megawatt gas turbines that are used in all kinds of things.
Wow, so this is some really impressive numbers in terms of the amount of data you're talking about taking in. And of course, I'm sure NASCAR is not exactly the most typical example. So I'm wondering if you could highlight some areas where you are seeing a need for this really intense data processing in terms of machine monitoring, and kind of outline for me what some of the typical requirements in those applications are.
Sure. Yeah. I will say though, I love my cars, right? I love my car projects with NASCAR, Porsche Racing Team, accessible autonomous bus for elderly and disabled, all kinds of other vehicles. The most common case for us though is working, people who make things, right? So people who make things use our technology, our products in the thing that they make, and they use them in the manufacturing of the thing. And so whether you're talking about, autonomous tractor, CNC machines, robots, autonomous vehicles, all of these kinds of things. And so for the machine monitoring, think about, any rotary machine, compressors, CNCs, conveyors, all of these things. I know a lot of people go straight to the whole predictive maintenance topic, and, that's interesting, but I tend to think more of just, what is the health of this thing? Like right here in the here and now, what is the health of this particular asset? And there's a lot that you can tell from the analog data. We can drop in like our MCN 100 product. We can drop in these high quality analog sensors for vibration, pressure, voltage, temperature, all kinds of things, right? There's 100 different sensors that it works with. And then we can also take telemetry from the machine itself. And this is where it gets interesting, is when you start to use these things in combination. And so, this is used today, a lot of factories around the world, and a lot of things out in the field as well.
Yeah, that makes sense. And I know one of the big challenges there is, when you're talking about adding new instrumentation onto an existing asset, figuring out how to connect that instrumentation is a relatively small problem because you can specify whatever interfaces you want. But when you're adding in the extra step of getting the telemetry out of the existing compute hardware, the existing management hardware, that can be a bit challenging. So how do you go about accessing that legacy data?
For the legacy data, we've been doing that for many years. The factory floor is where we live. So for 25 years now. So we've got we have hardware support for connecting to, the mod bus, the CAN bus, and all of these different legacy industrial interfaces from a, electromechanical perspective. And then from a software perspective, we have our ADLINK Edge software, which is runs on all of our Intel products, and that gives us things like out-of-the-box support for the Siemens, Allen Bradley, Rockwell SCADA protocol, the Modbus, Profinet, Pi Historian, so being able to stream data to and from OSI Soft Pi Historian, and all of these other things that you run into in a manufacturing air warehouse or other kinds of operations environments, right? So like, oil rigs, refineries, and even things around the wind farms.
Yeah, and if I'm not mistaken, ADLink even has an offering where you can scrape data off of a display. Isn't that right?
The decks, yeah. So that's a fun product, actually. So there's a lot of equipment that we find at customers that is new enough and modern enough that it has a digital display, a keyboard, and sometimes a mouse. But it's old enough that it doesn't have any open standard interfaces, right? There's no OPC UA, there's no DDS, there's none of these open standards that you see in modern systems. And so the engineer did something really clever with Intel. So this was a jointly invented product. And what you do is it's a little brick that you put on the machine, and you take the keyboard, mouse, and video, and you plug it into this brick, and then you plug the actual keyboard, mouse, and video into the other end of the brick. And what it does in between is, while you're using the system, it screen scrapes the display. So it does OCR using Google's Tesseract OCR library. We do OCR on each video frame, right? So think like 60 frames a second, 30 frames a second. So we OCR the video frames and convert every piece of data in the screen to an IoT telemetry stream, right? So then you can publish it via the DDS or MQTT. You can push it up to your clouds, the AWS and what have you. The temperature is, pressure is. And the really clever trick it does is, when someone's not using the machine, it'll actually script. It will go in and navigate to all of the screens of the application, of the equipment's user experience. It will navigate all the screens and capture all the data. So it doesn't need somebody sitting there driving.
Yeah, I really like that. It's a very cool little box.
It is.
One of the things that makes that possible is this whole notion of AI and machine learning, which has been getting so much traction over the last couple of years. It's really amazing how much that's grown, and not just for things like scraping these screens, but just the broader use for analyzing all this data you're taking off of these machines. So I'm wondering how you see machine learning and AI changing how people approach this problem of machine monitoring.
Yeah, it's definitely changing in a lot of ways. The most obvious one that everyone sees is the things around vision, so computer vision, right? So the being able to make sense of any situation, any problem that you can tell optically. So basically, if you can figure out a situation with your own eyes, then a machine can be trained to come to that same decision. Okay. For the data, the telemetry, we're able to do interesting things, like for NASCAR, they record tons of telemetry. And so in the course of, say, you do the Daytona 500, so you get all the telemetry from the Daytona 500, all the braking, all the acceleration, the G's, the change in engine load, all of these things are captured. And so then you can play that back on a dyno. So you can play that back basically with the real engine, but in simulation. You can simulate the entire Daytona 500 on a test stand. And if you know, like, this was the perfect run, this was the winning race, this was the perfect lap from the winning race, you can play that back through and you can look for deviation, right? So it can detect any deviations from that, and those can be flagged for the human. And the humans have a lot to do with that training, right? So one of the engineers I work with, Dwayne, he's been doing this for so many years. So he sits there, he's looking in the test chamber. It's like bulletproof glass in case when engines when engines at high RPM come apart, it can be a very kinetic event. So you're looking through the bulletproof glass into the chamber. You're watching, you're listening, you're looking at a display of all the telemetry. And, he's been doing this for so long, like, it kind of freaked me out. He leans over to me and he says, Joe, yeah, that that engine's going to come apart in the next 5 minutes. Like, he can just tell. But you need that kind of expertise to work with the data scientist to train, to do the annotation of the data, so that this human element's very important for making the machine learning effective.
Yeah, absolutely. And that's one of the things I think is most exciting about this whole field. It's pretty easy to get super focused on what the computers can do, but really what you're doing as much as anything is taking that expertise out of one person's head and making it accessible more broadly. And I think that's really, really exciting.
Yeah, it's more broadly, but even think about it as a tool for, not only can you take your most expert person and more broadly share that knowledge, but you can also take that knowledge and make it applied faster. So what if you need that same decision that he would have made, but you need that decision executed in microseconds instead of seconds? Okay, you need low latency interventions. What if it's optical inspection and the expert has trained you how to see the defects in these machine parts, but now by capturing their expertise and building it into these models, you give him a tool where when he goes to inspect the part, every suspect area is instantly highlighted, and then he can just click through them one by one, either accepting or rejecting each of those. And as he's doing so, he is continuing to refine, to retrain the model. So it's good stuff.
Yeah, very much so. And something we had talked about in earlier conversations is how this can turn an engineer into almost a superhuman, where you can respond so much faster, you can handle so much more of a workload, you can monitor so many more machines. It's really like gaining superpowers.
Very much so.
So of course the flip side to this, though, is that it does take a lot of compute hardware and some really intense software development and so forth to actually bring all these amazing capabilities to life. And I'm wondering if you can sketch a picture for me of what the compute requirements are for these sort of applications.
Sure.
And what ADLINK's delivering to help take on these just insane workloads.
Yeah, it's it's a different kind of workload, and you can scale to do that. Certainly Intel's done a lot with enabling the optimizing these kinds of workloads on Xeon and some of the higher class processors, being able to push some of those optimizations down into the smaller ones like Atom and Intel Core and what have you. But a lot of it actually requires different compute. So instead of just more compute, think about it as needing different compute. So there's some pretty specialized hardware out there, right? So you see things in the market. There's the TPUs, the GPUs, the VPUs, all of these things. And we work with all of those, and they are particularly well suited for these kinds of problems where can be highly parallelized and the like. So like we do a lot with the Movidius Mirrored X, with the OpenVINO. OpenVINO, it's nice because we can take the the test data, whether that be acoustic, telemetry, vibration, video. We use that to develop the ML models, or to help our customers with the tools and best practices around developing the ML models. And for that, it's your usual cast characters. It's your tensor, right? So that's TensorFlow, TensorLite, all of the variants there, PyTorch, all these things. Well, once you have a model that's trained, you can now take that and you run it through OpenVINO, which generates a quantized, optimized runtime that you use for the inference. And one of the things to distinguish here is when you talk about machine learning, you have training and you have inference, and they're asymmetric, right? Like training's very expensive and you do it occasionally. Inference is, in comparison, is computationally cheap, but you do it all the time.
Yeah, absolutely, absolutely. And I totally agree with you that platforms like OpenVINO have been a really huge deal for enabling these kinds of workloads. Among other reasons, the fact that one, you can address these very specialized kinds of hardware platforms like the Movidius.
Yep.
And then, of course, the fact that you can take all this work that you've done in the cloud, developing your models on very expensive, big sets of hardware, and turn it into something that is practical to run at the edge. The other piece of that, though, in my mind, we talked about this a little bit earlier, is just the raw amount of data that's coming in. And I think that also really points to why it's so important to do all this compute at the edge. So I'm wondering if you talk a little bit more about that. And I'm also curious, I had no idea that you were involved in the development of MQTT. That's very cool, and it's something we talk about on our site all the time. So I'm wondering if you can talk a little bit about like how you ingest all this data, where it gets processed, and how to keep the communications flowing. And maybe not such a big problem if you're just got a NASCAR engine on a test stand, but if you're talking about something like, say, a factory with distributed machinery, where and how you get the computing done, and where and how you traffic the data.
Sure. No, happy to talk about that. And just to be clear, MQTT was invented by my friends Arlen Nipper and Andy Stanford Clark. And so, they're the real geniuses behind it. One of my abilities is, I'm very quick to see value where maybe not everyone has, and then I get others to see it. So I took what was at the time a obscure proprietary telemetry protocol and worked with many others that together, and I did none of this by myself, but together we made it open standard, we made it open source, we convinced the world to adopt it. And that's, for talking to cloud, like thing to cloud, there's nothing better than MQTT. But what people need to understand is, in technology, everything is a tool, right? And if somebody asks you if it's a good tool, the correct response is, I don't know. What is it you want to do with it? Okay. So MQTT, it's not a panacea. It's not a cure-all. What it is it's a really great, lightweight pub sub protocol for talking to clouds, for talking over resource constrained or unreliable networks. And but it doesn't fit everything. And then you've got DDS, Data Distribution Service, which historically comes out of military and aero, and that's optimized around this UDP based multicast, being able to do high volume, extremely low latency, quality of service. So our work with DDS, everything we talk about is microseconds, right? At most tens of microseconds, not milliseconds. And so you start to look at using these things together. So I've got MQTT to the cloud, north-south, and north to the cloud, and then I've got DDS for what we call east-west, right? So how can things on a factory floor discover and work with one another and coordinate on manufacturing tasks with very low latency? This is why DDS is what's built into Open Robotics. So all of the ROS2 Open Robotics is built on DDS, and DDS that we contributed to open source, which is a Eclipse Foundation project called Eclipse Cyclone DDS is a tier 1 ROS middleware. So that's part of our contribution. So so you've got these protocols that helps you move the data, but where do you move it to? What do you do it with? We're big fans of train in the cloud, run at the edge. As I mentioned earlier, there's this asymmetric relation between the training and the inference, right? The training is done occasionally and it's computationally expensive. The inference is done all the time and it's computationally cheap. But the inference needs to be done on the data. And where's the data generated? It's generated at the edge. So we believe that the correct approach in most situations is going to be that you collect data at the edge, you bring it to the cloud as a training set, you develop and train your models, you publish those models back down to the edge, so then you have your runtime inference is happening on the data where the data is created. And we think that from an economics, that also works. So there's a brilliant university study that looked at if I'm using AWS, if I'm using Azure, what is the cost of doing video and acoustic analytics in those clouds, or with their technology, with their tools at the edge. And the answer was that it's 8 times less expensive to do it at the edge. But for me, even more interesting than the financial cost is the latency. So we deal with use cases where latency matters, right? If you have to take data to the cloud and do analytics and then bring decisions back, it's too late. The product's been damaged, the equipment is broken, the building's burned down, a person has been injured. And so that's why we really think the inference belongs at the edge in almost all situations.
So that makes sense, but I'm wanting to take a step back and think about the bigger picture here. So we've talked about a lot of different things, the volumes of data, where the data needs to be trafficked, the kind of hardware you need, the software development workflows. So it seems to me there's a lot of complexities involved in developing this advanced machine monitoring technology. So I'm sure there's a lot of ways for folks to go wrong. So I'm wondering if you've seen some common pitfalls and have some tips on how folks can avoid those.
Sure. We've all seen failed projects. Fortunately, they haven't been mine. And a lot of them, where they start to get in trouble, it's these, being so grand, so ambitious, it's like, I bet my business, right? Boil the ocean, all these euphemisms. And where I've seen people be successful is when they just pick, a business problem. Like, what is a business problem I have? And the business problem I have is at this one step in the manufacturing process, I'm getting too many false positives during my quality inspection, right? So maybe we just focus and hunker down and solve this. And because of that, the business impact is X, Y, Z, right? So they can talk about what it means in terms of revenue, productivity, customer sat, employee sat, injuries, whatever the metric is. And just focus on that. Just work that. Just pick a thing and just work that. And from that, you actually learn a lot that you can start to, once that's successful, okay, I was doing this for a particular step within a particular work cell in my manufacturing process. Now, how do I expand that to my inputs on the left and my outputs on the right? So, how do I start to expand it to other things within my manufacturing process? So when you take a very, kind of focused approach, that's where we've seen, customers be able to get a lot of success, get very fast ROI. And start simple, like just get the data flowing, right? Like I see people, they start arguing about which analytics tools, which ML framework, and all these things. And that is so cart before the horse, right? You're arguing about analytics tools and you haven't even seen any data yet. You haven't even opened the data spigot.
Yeah, that makes sense. Start small and go from there. So we're getting close to the end of our time, and I wonder if there's any closing thoughts you'd like to share with our audience.
Yeah. So, we had talked a bit about the analog data, vision. Vision is a great general purpose sensor. You can use it for a lot of things, but not everything. So, it doesn't capture the entire picture. So, think about when you're in an environment, when you're on a factory floor, what do you see? What do you hear? What do you feel? So there's not any one sensor that gives you the complete picture, right? So how do you use these in combination? How do you do things with sensor fusion, sensor fusion is a more accessible topic than most people might believe, and we can certainly help you with that. So if you want to do things like, combine the video analytics with the acoustic, with the vibration, and pull telemetry, pull data off of your existing legacy um, uh, manufacturing equipment, PLCs, SCADA, all of these kinds of things. We have our ADLINK Edge, which supports over 100 legacy protocols right out of the box. We can really work with you to help you figure that out.
Excellent. Well, that just leaves me to say thank you for joining us, Joe, and ask where our listeners can find you online.
It's not hard. If you Google Joe Speed IoT, I think that's like something stupid like 1 million hits. On Twitter, I'm Joe Speeds, like he goes too fast. And feel free to hit me up on LinkedIn as well. So always happy to help anyone here in the community.
Thanks so much for listening. As always, if you enjoyed listening today, please make sure to support us by subscribing and rating us on your favorite podcast app. And if you want to chat more about industrial technology, make sure to tweet us at insight.tech. This has been the IoT Dev Chat Podcast. Join us next time for more conversations with industry leaders at the forefront of IoT design.